So welcome everyone to the machine learning crash course. So just to give a brief overview on what machine learning is. Basically, the premise is just to learn from examples and data and then apply that gained knowledge into different and unique scenarios. So to give an example of that, it would be to learn from previous historical data on which kind of people are more susceptible to cancer, and then using those data, we can then apply to future predictions. So by looking at someone's health records, we can predict if they're more susceptible to cancer or no. Okay, so there are some key terms that we should understand in order to understand how machine learning works. So there is this term called labels, which basically means that we're trying to label a prediction on each of the set data we get. So for the previous example I talked about, the label would be the prediction we're putting on a person, whether they're more susceptible to cancer or not. And the features will be the input data. So input data can be separated into different categories like, let's say, height, weight, heart disease, and some other things like that. And yeah, examples are also very important to understand. So there's two kinds of examples. The first one is a labeled example. So this is more important in the training part because our machine learning models can see which kinds of features match with which kinds of labels. And then we can match them together to see if our prediction is right. Unlabeled examples is also good, but it's mainly for testing because we want to use these unlabeled examples to our advantage, right? We want to take these into our models and then produce a prediction on our own. Okay, and there are also different models that we can be using depending on the scenario that's presented. So for the regression model, we're basically predicting continuous values. So what that means is we could, for example, see how well students are doing at school, and we can predict what their final grade will be, something like that. And classification model would be to predict discrete values. So this I will explain a little bit more later, but it basically produces a value between 0 and 1. So this would fall into the cancer one, where we're predicting if they have cancer or if they don't have cancer. Okay, so we can start off with linear regression. Linear regression is basically an algorithm that's used to find a linear relationship between features and labels. So I'm sure you guys are all very familiar with this formula, y equals mx plus b. This is basically a simple way of actually just using machine learning and predicting some values. We can input the data as x, and then depending on the slope that we get and the b value, we can produce a y value. And something that's also very important for machine learning is to train and then take care of the difference between our predicted value and the actual value. So loss is a term that describes that. Loss is basically a number indicating the prediction's accuracy. And as you can see, the formula for that might seem a little bit confusing, but I'll try and explain. So basically what we're doing is here you can see that we're doing y minus prediction x. What that means is we're basically subtracting the actual value from the value we predicted so that we can get the value of difference between those two and see how much loss we have. And we're going to square it since it might become negative. And then we want to accumulate all of those losses and divide it by how many ever inputs we have so that we get an average loss of our data set. And also, just in case you guys have any questions, then you guys can send in the chat and I can respond to those. So training is also very important since we're going to try to learn optimal values for the M and the B value that I just talked about and the different weights of the features so that we can minimize the loss. So there are several ways that we can reduce the loss. So after collecting how much loss our model has, there's 3 different ways where we can decrease that value. So the first one is called gradient descent, and a lot of different scientists actually use this one. This is probably the most common one, and it's basically an algorithm that calculates the minimum. So as you can see on the right, there's basically a graph between loss and the value of the weights. So I will get a starting point. This is where my loss is currently. And then I will adjust the value of my weights. So basically weights are the M value and then the B value. So I can slowly adjust those and see where my loss ends up. So let's say my loss ends up here. So it's closer to where there will be 0 loss, which is around here. So if that's true, then I'll keep on moving the weights down so that I approach this this lowest point. So that's how the gradient descent works. And stochastic gradient descent is also kind of similar. Basically, it's the same concept, but except we are trying to take one input at a time. And you can imagine how this will take like much longer than the first one, since we're gonna take one data point at once. So let's say if I have 1,000 inputs, I would have to run 1,000 times. So this strategy isn't the best, but it can be useful in some cases. And a mini batch stochastic gradient descent is basically taking a smaller batch of data instead of all of it. So here in gradient descent, we're basically taking the loss of the entire batch of data we have. And mini batch stochastic gradient descent is basically taking part of it. So we have the advantage of having not just one data point, but also some of it without it taking so long. Sure, I can send the presentation link in a second. Can you guys see my screen or? Okay, so I'll continue. Okay, so one of the most popular devices that scientists will use for machine learning is called TensorFlow. So basically, it's an open source platform for machine learning. And open source basically means that not only can the developers access TensorFlow, everyone in the public can also use it. So this is just a small graph to explain how it works. So we have different classes, keras, layers, losses, metrics. So these are basically the main functions that we're going to be using. And these are the things that manage CPU, GPU, and TPU. Okay, so using TensorFlow, we need to have some hyperparameters. Basically what that means is, in addition to the weights that we're doing, we also want to have other variables to control how our machine learning model is learning. So the first one is called learning rate. Basically what this means is we're gonna see how much we're gonna step by. So if you try and remember the graph that I showed with the parabola like this and the loss, the learning rate basically controls how much we're going to go by every time. So this is important because if we overshoot the learning rate, then the loss will go from here all the way to the other side, and it will be also too high. And we want the right learning rate so that it goes slowly to the center and then swings backwards until it kind of finalizes at the lowest point. So that's why learning rates is also very important. Epochs is basically a term that describes how many times you want to train the algorithm. So each time we try to minimize the loss. And the batch size, as I explained before, it kind of controls like how many examples I want to take with my batch. Okay, so generalization is basically a term that describes how complex a model is. And the less complex the model is, the more accurate the results will be. And it kind of sounds like contradicting, but in theory, it is very true. Because if the model is too complex, then it will overfit to the training data. What that means is our model will only predict the right results for the data that are labeled. So for example, in the cancer case, if my data for training that are all labeled are of old woman, and my model is very, very good at overfitting and predicting the right results for old women, then when new data sets come, let's say a young boy, then they wouldn't be able to predict that case well. So actually, the less complex the model is, the more accurate the results will be. And examples must be drawn independently from the data set, and the distribution within the data should remain the same. So what that means is we have different kinds of people. So as I said, like elderlies, we have adults, we could have teenagers, and we don't want all of the same group of people in the same kind of data set. So when we're training, we want to separate our data sets into two kinds. So the first kind is called training. So this trains our models. And the second one is called testing. So after our model is trained, we want to make sure that our models are predicting the right results. So that's why we want to use the model to check with the test data to see if we're actually predicting the right results. So the distribution within those two data sets should remain the same. We shouldn't have all the teenagers in the training data and all of the elderlies in the test data, or else our model will be very inaccurate. Okay, so I kind of explained before about the training data and the test data. And something to keep in mind is that the larger the training set, the stronger the model will be. And the reason is because the more data that we can train with, the more our model will learn and adapt to different situations. So the more data we have, our model will be stronger and stronger. And the larger data set basically means that we have more things to test our model with. So as you can see, there will be more confidence in evaluation. And we should never train our model with the test data because we want to save that for checking how accurate our model is. Okay, so you might be wondering, we already have two sets. Why do we also need a validation set? So this is also important because we want to make sure that, again, it doesn't overfit to just the training set and the test data. We want another set called validation set so that after we test out our models and then we tweak with it, we can test it again based on the validation set. Okay, so I can just pause here really quickly for any questions. And yeah, you guys can type it out in the chat. Okay, it looks like there aren't any questions, so I'll keep moving on. Okay, so representation is also very important in machine learning. There is this term called feature engineering, and what it does is we want to take in the raw data we get. So it's normally in like Google Sheets, Excel sheets, and we want to take that and we want to change it so that it works better with our machine learning models. So there's this term called one hot encoding, which basically turns strings, which are basically words, to floats that are numbers. So it's harder for our computer to work with words than it is to numbers because we can take those numbers and we can easily use them to calculate stuff. And words are kind of hard to do so. So something that machine learning scientists do is that, let's say the input is Shorebird Way. So as you can see on the right, that is the street name of one of our, like, let's say one of our families. So then we can take that word and then we can change it into numbers. So there is this data type in computer science, which is called a vector or a list. So it keeps track of a list of all of the numbers. In this case, we can have and generate a new and unique list for each word. So in this case, Shorebird Way can be simplified into a bunch of zeros and ones. So this is why one-hot encoding is so important. And we also want to choose good features. What this means is we don't want to have unclear features. So let's say we have an input data that has all of the information about a teenage boy, but it is not labeled, or it is not clear if they ever had cancer or not. Then it would be bad to include that in our data set because it's not clear to us, and it can have zero values. So yeah, and also binning is also very important because when we want to group things together very easily for the computer to test out, we use binning so that we can kind of use a graph and see like where values are, and then we can group them together so that it's easier for the computer to calculate. Okay, so regularization is also very important for machine learning. Basically, what we want to do is we want to decrease the complexity, as I mentioned before. So this is an equation for how to basically decrease or reduce the chances of overfitting. So we basically want to minimize the loss and at the same time the complexity of the model. So there is this very common formula called the L2 regularization formula that basically minimizes overfitting. So basically what it does is it's kind of collects all of the different values of the weights. So as you can see before, that would be the Y value, that would be the B value, and then we want to basically minimize that. Okay, so we're going on to logistic regression, which is different from linear regression. Linear regression, as I said, can produce values that are not just between 0 and 1. But in this case, logistic regression have to calculate values that are 0 or 1. So we're going to use something called a sigmoid function, which you can see on the right. And basically what that does is if you graph it on, let's say, Desmos, you can see that the line kind of goes from this, and then it goes up, and then it kind of stops at when Y is 1 and when Y is 0. So that ensures that our value that we generate is going to be between 0 and 1. Yeah. Okay. So in linear regression, we use something called square loss, right? We squared the different differences between the right value and then our predicted value. And in logistic regression, we're going to use something called the log loss. And even though even if you haven't learned about log, it can be explainable. So basically what we're doing is we are subtracting 1 from our predicted value. So let's say we predict that this patient doesn't have cancer, so that'd be 0. So 1 minus 0 would be 1. And because we predicted 0, then this whole section would also be 1. And it kind of puts everything together and generates out a loss value so that we can try to minimize it to improve our model. Okay, so along with logistic regression, we also use classification. So what this does is, Logistic regression returns a probability between 0 and 1. And we use the classification model to turn that probability into a binary classification between 0 and 1. So for example, if my model generates out the percentage 0.67, then that would mean that there's a 67% chance that this person has cancer. Then we use that value and we turn it into either yes, he has cancer, or no, he doesn't have cancer. So that's basically what classification is. And we can also evaluate the model by testing our accuracy. Because the values we're getting are either yes or no's, we can see how many numbers of correct predictions we have over how many total predictions we're making. So this kind of goes into a dynamic of how we can truly see if our model is accurate, because let's say all of our models are basically predicting that no, this person has no cancer, and all of our data sets are similar. None of the data sets we're getting actually have people that have cancer. So even though that our model is just predicting no every time, the accuracy is actually very high. So if we use the strategy before, then it wouldn't really work. So we have these 4 different values that can ensure that our model is actually accurate. So a true positive is basically when our model predicted that it's a positive and the data actually shows that it's positive. And a false positive means that our model predicted positive, but it was actually negative, so we got it wrong. And a false negative basically means that our model predicted negative and it was actually positive, so we got it wrong again. And a true negative is when our model predicted negative and it was actually negative. So there's 2 different ways that we can calculate accuracy. The first one is called precision. So this would be out of how many times we predicted positive did we get it right. So this would be true positive over true positive plus false positive. This basically means out of all of the positive values in our data set, how many did we predict is true? And the same thing goes for recall. What proportion of actual positives were identified correctly? So this would be true positive plus false negative. And we're basically seeing how many of the values are actually correct in the data set, and also we predicted it. Okay, so in classification, there is a prediction bias. This basically means how far apart the 2 averages are. The averages basically come from our predictions and our labels. So after we calculate the bias, we can kind of identify that either our data set has a problem or our data set is okay. Okay, and I'll take a break right now to see if anyone has any questions. Okay, looks like there's oops. Yeah, looks like there's no questions, so we're gonna move along. Okay, so all the complicated stuff are basically logistic regression and linear regression. And neural networks is also very challenging to understand. So another way to make more complex models is through neural networks. And this is different from the linear models that we were talking about, because this one is nonlinear, and it comes from an activation function. Basically, that means we're going to generate something that doesn't always follow along. So if you have learned this in middle school, you can understand that a linear regression model kind of goes like a straight line. So depending on how much value the y is getting increased, it's going to proportionally increase the x value. But a nonlinear function is different. Even if y values are getting incremented by 1, x values might not be always incrementing by the same number. So this is helpful because we can have more kinds of results. And neural networks also have things called hidden layers, which are basically layers in the model that produce an output, which becomes another input layer. So before, we were just predicting a value. So using the data set that we have, we want to predict if, like, let's say a percentage, whether a person has cancer or not. In this case, we're gonna send in our results as the input as to another layer of testing. This kind of ensures that our accuracy goes up. Okay, so there are different kinds of neural networks. The first one is called multi-class neural networks, and there's two kinds. So multi-class neural networks is basically something that can classify a lot of things at the same time. So before, I have a program that predicts if someone has cancer. Using neural networks, we can have a multi-class version of that. So let's say we could now predict if a person has cancer, if they have a heart disease, if they have pneumonia, something like that. We can predict different results at the same time. So the first way to do that is something called one versus all. And what that does is we're going to build separate classifiers for each case. So before, we have one classifier for the cancer case, we're going to build 3 for pneumonia, heart disease, and cancer. And this could be bad because if we have a lot of different cases, then we're going to build up the storage in our computer, right? We're going to have to build a lot of different classifiers. Softmax is another approach to this. And we're going to build one classifier that basically generates a value out of between 0 and 1. And it's basically going to be a decimal probability. And using that probability, we then sort out into, okay, whether this is pneumonia, whether this is heart disease or cancer. So softmax can be more beneficial when there are a lot of different cases because we don't have to keep building different classifiers for different cases. Okay. And it looks like we're running out of time, so I'm just gonna skip through these harder ones. Okay, so I think this is pretty important for anyone that's trying to learn more about machine learning. Data dependencies are basically something you want to make sure of when you're kind of testing with your model. So reliability is basically standing for if our data set is reliable. If we got our data set from a very unreliable website, then some of our inputs might be flawed, and it would be bad because then if we are pushing it into a website, then we'll be predicting wrong values. Versioning is also very important because let's say we got data from a very old website and it doesn't actually match with all of the data sets that we have in the real world right now. Then our model will be out of date and it will also predict different results. Necessity is also very important because when you have too much data, then it'll be very bad for the computer and it'll take a long time to process all of those things. So we want to make sure that the data we actually need is going to be included and we don't need irrelevant information. So let's say where somebody lives when we're predicting cancer, that's not very important. So we want to make sure that we leave those data out so that we can include more important information. Correlation is also very important. It's kind of similar to necessity. It basically stands for if the data inputs are actually important in producing the right result. So in this case, sorry. in this case, where someone lives does not correlate to whether they can have cancer or not. And feedback loops are basically something that takes in user feedback to see if our model is actually still predicting the right results on the website. And if we are not, then we want to make sure we're changing things. And I will just talk about the last slide, machine learning systems in the real world. So as I said before, there could be cancer prediction, but also literature, surprisingly. A lot of people can use machine learning models to predict next word predictions. So when you're typing on your phone and something pops up on the top of your keyboard that says, okay, you might be able to just click on that and it matches the word that you're going to say next. That's using machine learning models. And it could also be applied to different books. So by seeing which sentence comes from a certain book, we can identify and see, okay, this kind of sentence and this kind of writing style is mostly common in this kind of literature. So machine learning systems can be applied to a lot of different things. And yeah, we're basically done here. If you guys have any questions, then you guys are free to ask them. But for now, I'm going to stop this screen share. And